set up, and we're going to start there today. So I'm not going to waste any time because we also have a lab we're going to do today. So I want to go through kind of the set of things that I expect to be able to do with this problem. It's not particularly hard, but if you've never done one before, it can have some intricacies. Also, like I said, not having a particularly good morning, so I will likely be calling on you guys. Don't be the person who says I don't know. Be the person who says I need your help. That's better. But be prepared for me to just call you out. And I have every intention of calling out the people that I think don't know the answer or are not paying attention. Let's just say that this is my answer to not doing corporal punishment. But I have been thinking quite seriously that it's probably time for us to have a quiz where I test your abilities before a test. So I'm thinking Friday is a good time for that. Hope you're working on your homework, because that seems like the appropriate place to start. This is a boom arm problem. And if you haven't done your homework yet, then you haven't seen one of these yet. But there's one that's in your homework. It's pretty early on. And I want to talk a little bit about what the conditions are for solving a boom arm problem. It's not much different than yesterday's bridge problem. But because of some of the slight variations that are here, there are some things that might make it different from what you've seen. The bridge problem, everything was kind of lined up and nice and horizontal. And of course, here that's pretty close, except for the cable that holds the boom in place. But that doesn't have to be how this problem is done. There's more than enough examples of booms that have, let's see if I can do it, where the boom arm is kind of at an angle, something like that. So just having the boom arm horizontal is a convenience factor. It doesn't have to be like that. In fact, many cranes start with the boom up and they lower the boom into place. So just understand that we're looking at a particular style of question, but there are definitely alternatives that are slightly different than this. Generally, there's 3 or 4 parts to a boom arm problem. And there's usually where the cable is attached. It might not be obvious why this is true, but changing the point of attachment of the cable can substantially alter the force that cable experiences. And there's the idea of maybe moving the attachment point on the boom, but not the original point where it's connected to the wall. That increases the angle, but also decreases the leverage because the torque arm length has gotten smaller. And we know that in dealing with torque, the torque arm distance and the angle both play a role. There's also how you could have a parallel cable, and they might ask you to compare these 2 cables. Well, here the angle stayed the same, but the torque arm distance is radically altered. This one clearly is going to increase the tension in the cable because I'm pulling on the boom arm in a much less advantageous location. The further out you can go, the better. You know that from opening the door. The further away you can push from the point where it turns, the better for you. Same idea here. At the same time, there's generally a load placed on the boom arm. Where you place the load on the boom arm makes a clear difference. The closer the load is to the wall, the less of a torque it's applying, the less tension is likely to be in that cable. You start putting that object further and further away from the wall, the harder it's going to be to hold that cable in place. So those kinds of things are kind of the qualitative analysis of how the boom arm operates, but we need to look at the pragmatics. So let's take a look at a relatively straightforward boom arm question. Let's do a 50 kilogram box being held by a 100 kilogram boom arm. Let's say the boom arm is 10 meters long, and this is placed 3 meters from the edge. And let's do the extra and have that 30 degrees. So I'd say that this is a relatively straightforward, setup of a problem. There's only 2 real questions related to this exercise. And I'm going to call this an exercise because it's not much of a problem. We're going to try and find something out. So as an exercise goes, you're probably looking at 2 possible questions. The first one is what's the tension in the cable holding the boom arm? this thing, what we're talking about. That's the most likely low-hanging fruit kind of question. Of course, there's also going to be questions about how much force the wall is applying to the boom arm. That's not dissimilar. We're going to look at both questions and get an idea for how to solve them. But again, it's very similar to what we did yesterday. So I want to start by reminding us a couple things. We get to look at net force and net torque on a problem like this. And we're assuming a static condition, so net force is 0 and net torque is 0. Some of this might be easier to use in solving this problem than others. Next, the system isn't moving, so we get to pick a pivot point. Now, here is where I would encourage you to think long-term about your problem. I can choose anywhere I want for my pivot point. If I'm solving for the tension, I probably don't want to place the pivot point at the end here, because that eliminates the tension from being portion of the problem. And so it would not serve the purpose of finding out what the tension is. At the same time, I don't think placing the pivot point somewhere in the middle is helpful either. I really don't know what the wall is doing. And the wall is a series of unknown forces. That's probably a bad place to place the torque arm too. I'm sorry, place the pivot point. And although I know the wall probably pushes this way, the wall might also push upwards or downwards. So although this force doesn't cause a torque, these two might. And without knowing whether those are there or not, that makes placing the pivot point anywhere but the edge probably a bad idea, which is why the best place to put our pivot point is at the natural pivot for this problem. It eliminates the wall's contribution to the torque and allows us to focus only on the other torques that are acting on the system. So with that pivot point, I'm going to try and make this smaller so that I don't have it taking up so much space. I want to kind of set up the problem. Would you all agree that there are 3 torques that act on the boom arm with the pivot point at the wall? If you all agree, then you should be able to set up a torque matrix, I guess. I've been doing this the same way for a little while, but I had some students that were really confused about what I was doing. So let's see if we can't identify the things that are causing a torque to the system. I'm just going to call on people because I'm really in a mood and I want to make sure everybody's involved today. So give me a second. I'm just going to bring up my roster so that I'm being at least relatively fair. And then I'm going to call names based on where my finger lands instead of just being, mean. All right. Tucker, can you tell me one of the torques?
The weight is 50 kilogram weight is.
Okay, that's fine. That's enough. All I'm asking for is what things are causing torque. We'll set up the rest of this in just a minute, so I'll circle back. All right. Sophia, can you tell me something else that is causing a torque? All right, so the arm itself. Fantastic. Maddie, can you tell me something else that's causing a torque? Excellent. I think these are the 3 things that are causing torques to the boom arm. Now, there are 3 parts to torque. I've been writing this like a little matrix this whole year. I did this for work, and now I'm doing it for torque. Anytime the calculation of something is more complicated, I kind of lay them out in this way. And then yesterday, I indicated that, well, these add up to be 0, and somebody really didn't understand what the whole thing I was trying to do here was. I'm quite literally trying to say you add these 3 things together and set them equal to 0. That's all I'm trying to do by setting it up this way. I'm trying to help you realize that there are 4 things that you have to consider for each of the torques that are here. You have to consider the size of the torque arm. You have to consider the size of the force. You have to consider the angle between the force and the torque arm. And you have to consider whether it's positive or negative. 4 things you have to consider for each torque. That's a lot more than we did with force. So I'm trying to help you lay this out. Now, some of you really do struggle. And although I think part of that is because it's hard, part of it's because you only hear parts of what's being said. Maybe it's time for shaking up the seating chart. Get people closer to the front of the room. But I also want you to realize that there's 3 things here. I've been saying this for a little while now. Look at each one of these. Flesh it out. I'm going to step back for a minute, be quiet, but then I'm going to call out, looks like 9 people, right? And then we'll deal with plus and minus after that. So torque arm, size of force, and the angle in which it occurs for each of these 3 things. I'll be quiet now. Everything seems great, but the mistake might be subtle. And so let's try and talk about this for just a minute, because a lot of you didn't suggest there was a mistake here. And this might be my fault. When I'm trying to indicate this torque, this is the weight of the bar. By putting the weight and the torque arm length is 10 meters, we're suggesting that the weight of the entire bar is concentrated here. And that's not true. So if I haven't said this, then maybe add something in your notes here. For an object with extension like this, an object that takes up space, the weight acts at the center of mass. Now, I didn't say anything special about the arm, so you had to make an assumption. A good assumption to make is that the center of mass is in the center of the object, which would suggest the weight would be acting here. So I'm going to change that 10 meters to 5, because that's the middle of the bar. You okay? No, I didn't say anything about that. I wasn't explicit about that. But now I hope you have something in your notes that will help you for the next time. Yesterday we had done that with the bridge, but I'm not sure I made a big statement about it. All right. Well, since she was already put on the spot, Ella, why don't you pick another one? Tell us about it.
50.
All right. What do you want for the torque arm for that?
7.
Okay, 7 meters. Jonna, what am I going to use for that force?
50 G.
500. And Jake, what am I going to do for the angle? All right. That looks great. So, Lorena, what can we do for this last one?
So I know the force, it would be T sine 30, but
Okay.
the center of mass force can throw me off with the tension.
Now, for this one, this force is what determined where the torque arm was. We say that the weight was acting at the center of mass, and that's why this was 5 meters, because the force of gravity acting on it it's not concentrated there, but we've established that weight acts at the center of mass of objects for mathematical purposes. Now, the tension isn't connected at the middle. The tension is applying a force at a specific location on the object. So for the tension, we would use the point of attachment. So that would be the 10 meters. Is that good for everybody? All right. We have to assign positive and negative to torques now. The 4th thing. And I'm going to tell you that I want out of the board to be positive. So that means you have to use my convention to determine which of these are positive and which of these are negative, and there's a right answer and a wrong answer now. So you can either use the old 3-finger salute or the whole curly thing, but out of the board is positive. So I want to see if you know how to do this. And go ahead and label them positive and negative based on that. Again, out of the board towards you, is positive. Alrighty. Those are the right answers. Do I need to explain it to the class?
Yes.
Okay, just want to check. So you have two options here. Let's just pick one of the torques. So I think if we pick one, the rest will kind of fall into place. I'm going to draw the torque arm as an arrow from the pivot point to where the force is applied. Now, you guys who have your paper in front of you, it's a 3-finger rule, and it's R cross F, which means your pointer finger points in the direction of the torque arm, and your middle finger points in the direction of the force. They are attempting to establish a plane, and your thumb points perpendicular to that plane. You have an arrow pointed to the right now, and you have to use your right hand. And so you're trying to do something like this. Just turn your paper so it points away from you, and then you can point away from you. You will find that works a lot easier and will make this much easier for you to do. Now, I'm saying that because I'm going to walk over to the board, and I'm not going to make it awkward for me. I'm going to make sure I can point away from me. And now what you do next is leaving your pointer finger pointing in the direction of R, you rotate your wrist until your middle finger aligns as closely as possible with the direction of the force, which for us is going to be downwards. My thumb then points into the board. That's what makes it negative. Now, you could use the curl rule too. If the only force acting on this was that gravity downwards, would you agree that the boom would do that? So I curl my fingers in the direction that force makes the boom go, and my thumb points in the direction of the torque, which is also into the board. Everybody good so far? So if I consider the tension at the end, wouldn't you agree that the tension is trying to pull the boom arm upwards? Upwards. My thumb points out of the board. Or R, F is this way, but still it's above the bar, and my thumb is out of the board. Out of the board positive, into the board negative. Is that okay? Better? The only time that's ever going to be an issue is if they specifically tell you what is positive. But they will do that. It's happened. So you need to be able to use the right hand rule to comply with their directions for positive and negative. I believe we're done here. You have to figure out T now, which is just a little bit of arithmetic. So if you haven't already done so, fire up them mental things and do some work. It's not hard. This one is probably something you could do in your head. Add them up, set them equal to 0, solve for T. Did you? That's what I got. So I'm glad. Now, if you use 9.8, yours is a little different. It's a little less. But I kind of picked these numbers because I knew it would work out. So 1,700 newtons works out okay for me. Now, any questions about this one? This was pretty straightforward. Let's advance this a bit. Because I think asking how much force does the wall apply is a good follow-up question, and one that I would like to show you how to do. We now know how much tension is being applied to the, to the rope, 1,700 newtons. And it's being applied at an angle. And so we know some of that 1,700 is just to the left, and some of that 1,700 is straight up. Does that make sense? Now, at the same time, there is 500 newtons downwards and 1,000 newtons downwards. The thing, what it comes down to is the wall has to be acting in such a way as to maintain this balance. If the wall wasn't applying a force to the boom arm wouldn't stay here. It would probably be traveling into the wall and upwards or downwards at the same time. So there's clearly going to be some force that the wall has to apply. I don't think it's hard to imagine that the wall has to push outwards on the boom arm. I think that's pretty easy to imagine. With the string pulling to the left, the wall has to keep it from going into the wall. But whether the wall pushes upwards or downwards, that might be harder to do. The real issue is that if we decide to solve this problem using torque, you might think we can put the pivot point someplace else and then deal with net torque. The problem is that you really can't. And here's why. We don't know what this force is. And therefore, we don't know the size of the force, nor the angle at which it acts. We might be able to get one of the components using this method, but we're probably not going to be able to get both, because that force likely acts at an angle. And that would give us two unknowns, the size of the force and the angle at which it acts. So, not going to be able to use that method. But there is a method we can use, and it's really pretty straightforward. First semester, two forces acting downwards, a force acting at an angle, and the wall. I don't know what direction the wall is acting, and I don't know how big the force in the wall is. So instead of drawing just some force like here, because I know the net force has to be 0, I'm just going to say that there's a bit of force from the wall to the right, and I'll call that wall in the x direction. And I think from looking at this picture, there's going to be some wall in the y direction. I'm just going to put those in there. Net force has to be equal to 0. So net force in the x direction is going to be 0. Net force in the y direction is going to be 0. Not much to do here. And we've done this problem plenty of times before. So I'm going to look closely and realize that the 1,700 will have to be broken up into components. I don't really feel like drawing all of that on here. I think you guys now know cosine and sine pretty well. So I think I can jump right to net force in the x direction equals 0. So Wx minus 1,700 cosine 30 equals 0. Am I okay to do that, or do I need to do the triangle stuff? Net force in the y direction, same thing. I've got W in the y direction. I've got 1,700 sine 30 in the y direction. Minus 1,000 minus 500 equals 0. This is just too easy not to do it this way. The torque way would just be way, way more work. And now, well, I mean, come on, this is easy. Well, easy-ish. Can you tell me what the wall's Y force is and the wall's X force? X force. Well, I believe you can. So, Jack, which one did you get?
I have the wall of the X direction first.
Go ahead.
1472.24.
Fantastic. Jaden, did you get the Y one yet?
Yeah, 650.
Excellent. Not terrible. Now, this probably isn't the answer. I think these are components of the answer. Like, I think you probably have to do Pythagorean theorem to get the total force from the wall. And maybe tangent to get the angle at which it acts on the boom arm. And I don't know that we have to do that. I don't think pushing the buttons to do Pythagorean theorem is necessary. But I do want you to realize that there's two components. This one came out to be positive. Keep that in mind too. So when I look at the boom arm, it seems to me that there are two forces that act from the wall. There's 1472 in this direction and 650 in this direction. There is a total force from the wall that way. Pythagorean theorem would tell you how big that force is and whether the cement could take it without crumbling. And then you could probably figure out that angle too. We don't have to do that, do we? So I'll leave that part to you guys because I can't bring myself to do Pythagorean theorem again. So that's the problem. That is a boom arm question. And that, I mean, aside from them changing a parameter, the box is moved a meter to the right or a meter to the left, refigure everything out. That's the problem. This is all there is. Now, there are other versions of this, and I don't want to, try all of them. But a boom arm question is still just a net force, net torque question. Pick a good pivot point, and the problem generally figures itself out pretty quick. We will have to eventually deal with this question, and we're not going to do it today, but I set it up yesterday. And so we talked a little bit about the fact that there's ladder questions. And a ladder question is, there's a whole kind of, there's a whole bunch of stuff there about these kind of problems. Right now, this ladder question, believe it or not, is not terrible. If I was to ask you, where could you stand and not have the ladder slide out from under you? That could be tough. Or, just what is the size of the frictional force holding the ladder in place? That would be easier. But note that there's other kinds of ladders. So some ladder problems are easier than others. Anybody have one of these at home? Yeah. I don't even like thinking about this problem. This actually could be tough, like figuring out what the tension is there to hold the ladder legs in place. That one can be hard. I don't even like thinking about it. So there are problems that actually are pretty challenging. This one's probably above the purview of our class. I mean, we could do it. It's just a lot. It's a lot of work. It's got a lot of things going on, especially the person standing on there. Figuring out this tension, it can be a real challenge, with or without friction at the base. Meaning, There's the version of this problem where you assume there's friction at the base, preventing the lateral legs from coming outwards, or you just put it on ice and there's none. It eliminates a couple forces, making it a little easier to work on. But like the forces acting here at this point, tough. They're pretty tough. So it's still a statics problem. We still have forces. You have to break this up into two different torque arms, the right side of the ladder and the left side of the ladder, and then work it from there, but it's not straightforward. So just be aware that we're looking at a very narrow subset of questions. There is a bigger universe of these questions. So we're going to stop all of that because you're going to take data. The data you're going to take is super fast to take. But in order for you to understand what it is you're doing, I want to give you at least a little bit of a heads up. You will need a roll of toilet paper. And I would go for one that's not depleted because some of them are beginning to get depleted. So choose one that's not. So there is a roll of toilet paper-ish. There. We already talked a little bit about this problem earlier when you had to figure out what the acceleration of the ribbon was. Do you remember? So this is a continuation of that. We're going to talk about the mechanics of this problem a little bit tomorrow, but today you're going to take data. And the data you're going to need to take is three things. You do need to record the inner radius and the outer radius. Diameter might be easier than radius. So if you got a meter stick in the back, you can do this. But then you have to measure the acceleration of the toilet paper as it unrolls. That's going to be more challenging. So to facilitate that,